So we are ready for the second speaker then, Friedhelm Hamann from the TU Berlin. He has been a student at this university and the Science of Intelligence Research Cluster since 2022, and he works with Professor Guillermo Gallego. Also, he just spent a semester at the University of UPenn collaborating with Kostas Danielidis. And he will present new algorithm using and extending the maximization framework for optical flow tracking and 3D motion estimation.
Yes, thanks Cornelia for this kind introduction. Exactly, so the title of the talk today is Motion Prior Contrast Maximization for Dense Continuous Time Motion Estimation. And again, I'd like to quickly introduce myself. So I'm a PhD student at Technical University Berlin, and also a research center called Science of Intelligence, where I work with Guillermo. And the reason I'm talking here today is because via this NeuroPAC fellowship, this really nice opportunity, I had the chance to go to Philadelphia for 6 months and to work with Kostas Danielidis at UPenn at the GRASP lab. And the motivation for this collaboration was that here in Berlin, we already work on animal observation with event cameras. We, for example, have recent work on action detection of penguin behavior, where we brought an event camera to Antarctica. If you're interested, you can check it out via this QR code. But we also work on other projects. For example, we have ongoing work on event-based mice tracking. On the other hand, in Philadelphia, Costa's group built this amazing smart aviary where they can observe a flock of birds with in total 12 RGB cameras, which are fully synchronized and fully calibrated, and they worked on 3D bird tracking. The idea was now to extend this and to use event data, like you can see here in the bottom, a sample of the data. And specifically, during this work on bird tracking with RGB cameras, they observed some common failure cases. And one of them is an identity switch, which is also quite common generally in multi-object tracking. So when you have two objects which are occluding each other, you could just switch identities. And the question is now, could we use event cameras to help with that problem? You see here exactly this case visualized with two birds crossing, and you see a different visualization of exactly the same sequence down here to the right, where we have like a spatio-temporal visualization of that scene. You have the image plane and then the events over time, and we really nicely see the two birds crossing here and the events that they cause. So one idea is here, if we can regress correct trajectories in this event volume, then could we really use this nature of the event, this continuous nature of the events, to regress trajectories and then disambiguate those cases that often occur in event cameras. And we want to take this as like a motivating example for the following task. And this is the task that we will talk about in the rest of the presentation, where the input is an event volume of about half a second. And we want within this same volume regress pixel level trajectories. So you see it here in the beginning, the wagon is on the right of the image and moves to the middle. And we want to regress those trajectories, like you see the trajectories here in red of the wagon. That's the task. Now, established inference pipeline can look the following way. The events are the input. We transform them to a voxel grid and put them into a neural network, which outputs our trajectories. And the trajectories are any continuous parametric function that can be, for example, Bézier curves or a linear interpolation of basis functions. So in practice, the output of the prediction is the per pixel parameters for our trajectories. And The only question remaining is now, how do we train this network? And the problem is that ground truth is hard, or if not impossible, to obtain for real world use cases. So if we, for example, think back of this motivating bird example, there's not really a good way of how we can get pixel level ground truth trajectories for this real data. We have several birds, they move fast, and they also show large deformations. We now have two options to still train a network, and both have their own shortcomings. The first one would be to train on simulated data. And this has been done before for this task. Data was simulated, and then we tried this recent model on actual data, on real world data, but what we see is that the prediction is quite different to the ground truth. So the shortcoming here is a limited generalization. The option 2 would be to use a self-supervised loss where we don't need ground truth. And one class of those losses is a focus loss or contrast maximization. The idea here is that we have events within a time window, which you see here a bit within the time window, the motion blur in this visualization, in this 2D histogram. But if we warp the events to a common reference time and we know along the correct trajectories, then we should get a sharp image, and we can use, it has been shown that you can use the sharpness of an image as an optimization objective. The shortcoming here with this option is previously this has been only estimated on linear optical flow data sets with a length of up to 100 milliseconds. So before I explain, we basically use the best of both worlds from those two options. But before I talk more about our method, I want to quickly reiterate a bit on this idea of contrast maximization. Essentially, what we know is we have the brightness constancy assumption. So we assume there is no change of brightness in the scene. And under this assumption, events are caused by moving edges. So if we have some events now, we have a motion model, which is parameterized with parameter theta. And if we know the correct trajectories, all events caused by the same world point, they should be warped to the same pixel position. And out of this kind of seemingly chaotic event volume, we should get a sharp image if we warp all events at one reference time. And we can measure this event alignment to get like a focus score. So on a high level, really, the sharpness of the image is a proxy of how good our parameters are. So let's include this in our pipeline to train this inference pipeline that I've introduced earlier. We extend this now with a self-supervised loss module, where the input to the loss module are the predicted trajectories and the raw events. We take the raw events, we somehow interpolate the trajectory, the warp with the trajectories, and then add the displacement for each event to the raw events to get our image and our training loss. The big question here is now how we need association between potentially millions of events and thousands of nonlinear trajectories. So this has been done before, but only for linear trajectories. For the nonlinear trajectories, it's not clear on how to do this assignment. So to explain this, let's look at this simplified plot of the assignment problem. We show it here in 1D, so we have the pixel position, at least one dimension, over time. And we have an event here, this red dot, at the event time t sub k, and we want to warp it to the event time t sub to the reference time. Furthermore, we have several trajectories around, here visualized 2 in blue, and we want to know now what is the warp for the event based on those trajectories. And our solution is to use a soft assignment via a k nearest neighbor approach. So for each event, we look for the k closest trajectories. And this is still very difficult because, as I said, potentially we have millions of events. Therefore, we don't calculate this for every event, but we compute a spatiotemporal lookup table. And in order to have a differentiable solution, we do the calculation using a framework called KOPS. Let's now look a little bit closer on how we do this k-nearest neighbor assignment. Essentially, we don't do it in spatiotemporal 3D space, but we do this k-nearest neighbor search in 2D in several discrete time bins. And this is what you see here visualized for one time bin. This is the image plane, and you see the position of the trajectories in blue. And then this grid structure is our lookup table, where for each entry of the lookup table, we now look for the k closest trajectories. For example, here are the 4 closest trajectories to this sample entry marked in orange. And then in the next step, we interpolate the displacement from the k closest trajectories for each entry. At that point, we have built the lookup table, and we can simply look up the per event displacement. And afterwards, we use the same step like in previous contrast maximization based approaches. The calculated displacement is added to each event. We see here the raw events, and then the warped events are added up to build an image of warped events where we use the sharpness. Specifically, we use the gradient magnitude as a loss. Now, I've said before, evaluation is difficult because we usually don't have ground truth for real world scenes. Luckily, there's this really nice data set called EVIMO, which contains several independent moving objects and ego motion. And they captured this in the motion capture lab and provide poses and also object models. And this allows us to actually calculate long-range point trajectories. And this is the data set that we evaluate our method on. To show the advantages of our self-supervised loss, we trained several models, namely a model which I term in-domain, one that we term zero-shot, and one is ours with a self-supervised loss. And all of them are pre-trained on the multi-flow dataset. And then they differ on how we train them in the target domain, on the EVIMO dataset. The first one, in domain, as the name suggests, is trained directly on this calculated ground truth. I mark it here with the yellow circle because we can do it here because we have this dataset captured in a motion capture lab, but usually this would not be possible because, for example, in case of the birds, we don't have ground truth. We have one zero-shot model, which means we don't have any training in the target domain. We just have the synthetic pre-training. And lastly, our model is in the target domain trained with our self-supervised loss. Now we can look at some qualitative examples. We have the ground truth. We have the in-domain model, which expectedly performs best on this data. And then we have the zero-shot model, which shows some generalization problems, which we can largely improve with our self-supervised loss, which is also reflected in the quantitative results. Additionally, we also evaluate on the DSEC optical flow benchmark. This is now a linear optical flow evaluation for 100 milliseconds. We still do evaluation here simply due to the case that all previous contrast maximization based methods evaluated on this data set. So we need to do evaluation here in order to compare to other methods. So you see here the visualization of the raw events of some scenes. And then if we warp the events with our resulting flow, we get sharp images. Moreover, you can also see here that in our method, you don't see any event collapse. This is like a common failure case where we have undesired local minima in our loss function. Furthermore, we can see here results for ERAFT, a supervised method for comparison, results of visualizations for the most recent self-supervised methods, and then lastly, our method, where in addition to, like, our model performs on most sequences best on the quantitative results, but here you can also see that it often delineates objects better than comparable previous self-supervised methods. Now, in the end, I want to be a little bit more mathematical to outline where our contribution lies in contrast to previous contrast maximization-based methods, and therefore compare to two other papers in this field. One is called Secrets of Event-Based Optical Flow from ECCV 22, and the other one, Taming Contrast Maximization, from last year's ICCV. So we can remember the warp of an event is the event position x sub k plus delta x sub k, the event displacement. And our method differs in how this event displacement is calculated. Here in the ECCV paper, they use a linear trajectory. In the ICCV paper, they use flow concatenation, which allows for some nonlinearity, but we are the first ones who use explicitly a nonlinear trajectory. Additionally, there are different ways to from the warped events to calculate the image of warped events. We use a histogram like in the ECCV paper. Another option would be a median timestamp image. And then one notable example, which we also extended, is, so I mentioned already, one of the common failure cases in contrast maximization is event collapse, which are basically undesired local minima. And so using this loss, it's really important to have good regularization. Regularization method introduced here in the ECCV paper was to use a multi-reference loss. So in one optimization step or one training step, we warp the events to multiple reference times. And they, in practice, used 3. And this was later extended to several partitions and multiple timescales, which gets quite complicated. So we simplify this by just using one random reference time at every training step, which has 2 advantages. A, over the course of the training, we truly have a sharp image at any reference time. And then secondly, it also, if you look at the loss function, simplifies the calculation, which therefore we use less VRAM in training, and we basically, it allows us to train the whole model without any, during the loss calculation, we don't need to subsample the events. Okay, and with this overview, I'd like to conclude the presentation. In summary, we provided a loss formulation for contrast maximization with a nonlinear trajectory prior. We introduced an efficient method to solve the assignment problem, and we showed results on 2 tasks. Task 1 was a trajectory prediction, where we provide the best model without using ground truth in the target domain, which is often not available. And secondly, on optical flow, where we show state-of-the-art performance on DSEC among self-supervised methods. And with that, I would like to conclude my talk. Thanks for your attention.
So thank you very much for this really interesting talk and so clearly explained. Do we have questions?
Yes. Well, I have one. I think it's quick, so I'll ask it first. So when you do this interpolation of the sparse trajectories, right, would it be fair to say that you've actually defined a dense flow field that which you can sample then per event?
Yes, I think this is a good way to think of it. Yeah.
Okay.
Basically,
So then
the trajectories are like maybe like a sparse flow field, if you will. And by the interpolation, we essentially have, I mean, it's still discretized, but it's like a dense flow field. I think what you have to keep in mind, like every entry of this lookup table is the flow with respect to the reference time.
Right.
So it's not like to the next flow. Actually, there's one thing that I not mentioned here. We use an additional regularizer where we also interpolate the flow field between two adjacent time bins, and we use this for regularization. But yeah, I think this is a good way to think of it. Yeah, it's like a flow field.
Got it.
A dense flow field.
Yeah. So then as you go forward or backwards in time, you'll have occlusions come and go, which means that the originally tracked points have disappeared, right? So then the interpolated flow field would put flow on top of new points that weren't in the original frame, correct?
Yes, that's true.
Okay.
I mean,
Okay.
occlusions is I think one of the challenges.
For sure.
Essentially, we only track the points because we center the trajectories at t0 or at the start time. Yeah, here. All trajectories are centered within its according pixel at time ts. So if there's new content coming into the scene during the time, we would not be able to capture it. Yeah, that's true.
Thank you. Thank you very much. Very nice talk. We have a second question from Shintaro Shiba. Why don't you have event collapse?
I mean, I think this comes down to several regularization techniques. One is the multi-reference times, where I think we show we have ablations where we can show that moving from like multiple reference times, like 3 reference times, to this scheme of randomly sampling the reference time improves the regularization. And then I didn't mention it here in the talk for brevity, but we have in our loss function, an additional regularizer where we basically infer spatial smoothness within our time bins. So I think it's just like managing those different types of regularization in order to minimize it.
Thank you.